some issues in terms of the linkage I was given. So, but I just want to make sure we confirm that we are on the same page. So this is a distributed system, isn't it? Please, someone confirm that. Okay. So fine. So I think sorry about that delay. But we can all now begin. First of all, I hope you are all doing fine. So I'll go off camera in a short while to ensure that we don't waste a lot of bundles, but I'll go off in a short while. But I hope everyone is doing fine. These are trying times, and I'm sure we want to ensure that everyone is doing fine. And also, I hope that the friends you know are also doing fine, and hopefully everything will be back to normal sometime. So in this group here, I think I have had a chance to teach the group from BTC. Computer science group, I have not taught them before. So some of you, that's why I decided to show my face so that at least you know whom we are talking to. You might have seen me on the corridors of Strathmore, but you didn't know who I am. But I think now we are going to meet. But the BTC group, I'm sure they can remember who I am. Of course, 2 years ago, I don't think I've changed much. Okay, so the course that we are going to deal with this semester is distributed systems. And before I go to the introduction, maybe I'll just mention a few things that I hope guys were already familiar with. So before we continue. So the background of this course is supposed to have been computer networks, and then of course operating systems. So some of the things that we'll cover in the course actually build up on that. So there's a lot in terms of computer networks. The building blocks of computer networks are key for this particular course. And then, of course, operating systems is key to this particular course. So, and computer networks, you did part of that in first year. And of course, you have done several other courses that are related to networks, I believe. And then operating system was, I think, second year. And therefore, I might have to make assumptions, but in some scenarios where you find that I am making too much assumption, feel free to request such that maybe I pick up something. So I want us to be all up to speed so that we can be able to understand and be able to have gainful period during this particular session. So maybe one of the things that I will, before I go far, why I mentioned the background is that this course at one moment can actually be very, very, very technical. So I would expect that if you have, please spare some time to look at aspects of computer networks. In our notes, we'll have to mention some of those. Maybe areas you might want to recap. And then you might also want to recap something on operating systems. So in some of those areas, I'll try to mention so that it is easier for you to be able to know which particular areas, to start with. But for now, let me just maybe pick up the area, especially with the slides, so that we can be able to pick up some of those points quickly. So I'll just go on my screen. I hope you can be able to see all that, okay? And this, for those who have not met me, I'm Professor Tea, and I'll be taking you for this particular course. So as an introduction, I always start with basic things, which I want us maybe to start with. Now, one of the first things that I'm keen about is, and I want you maybe later on, please feel free to be able to share that information on maybe on our chat, so that we can be able to ensure that we don't spend much time on this. So the first thing that I want us maybe discuss as a group to find me whom you want to call a module leader. So I want this person here will be my first point of contact. Maybe if you can do that for the 3 groups, I'll be comfortable. So maybe you might want to use the class rep, whichever you want is fine with me, but please choose someone, and I'll be glad even to have that shared during this class. So so the important point, so we need that any volunteer, or you can actually decide among them yourselves. And there are certain things that I will want to do. In a face-to-face scenario, I have cases where people work together as teams, and we see how well to do this. But in this scenario, we might want, I will not discourage people working together, but most of the time you might find that you might want to generally just might be offside to be able to talk to some of your classmates. So because I have several exercises that are there that I will want people to look at, we have several discussion implementation tasks, and then usually classmates are usually the first point of contact. So it's much easier if we utilize those groups. So now the next thing that is important, why are we having this particular course? So the key to this is that we want, most importantly, we want us to be able to understand the developments in distributed systems. So in ordinary life, you use a lot of distributed systems, but now we are going to spend time to be able to identify which ones are the developments in this. Now, but when you have distributed systems, of course, we have problems. Now, think of it this way. I might be speaking to maybe some of your colleagues who are in Nairobi, some are far. I don't know if some are even outside the country. So we have issues of timing, okay? So how do we ensure that those different times, the system does not confuse, okay? Then, of course, we need to be able to name, because each one of us is having a different location of access. How do we name them so that there's no confusion? So there's location and the naming of that. Then, of course, for us to be able to communicate well, we need to have inter-process communication. Inter-process communication is saying, like right now as I'm speaking, we are using a medium, we are using networks, we are using different kind of, for example, equipment, we are using tablets, phones, and whatever to communicate. So each one has different software. So how do they communicate? So we call that, from one to the other, we call that inter-process communication. We'll also spend time to understand how the distributed system organizes files. So we call that distributed file systems. And then we'll also understand peer-to-peer. Now, as we are chatting now, we have the concept of peer-to-peer, so P2P and group communication. So here we have a group communication. But I can also set up one-to-one, which is peer-to-peer, so that I have information being sent from one to the other. So that's called peer-to-peer. But this one, what we have is group communication. So we'll have to understand how, and this is a very good example of how we can implement some of this. Now, the next thing that we'll be able to look at in general, so we'll see what we refer to as what are the major topics. So we'll have an overview, and then we'll have communication complexity. Now, the communication, if you are receiving me, listening to me, and even if we are responding, you'll find that there's a lot of complexity involved. So how is that handled? So that is part of the things we'll look at. How do we design and analyze the algorithms that are used and protocols that are used for us to communicate effectively? So we call that distributed algorithms and protocols. We'll also have to look at what we call fault-tolerant protocols. Now, fault-tolerant protocols are saying, supposing, for example, you are working on one part and power goes down. What will happen to the other part of the system? Will it destroy all the information you had? Will it mess up all your files? So that is called fault tolerance. So it makes sure that when something happens, maybe shortages, whatever, power outages, that in the end, your information is stored quite well. And then synchronous computations, whereby if things are being done, how do we ensure that they are in an orderly fashion? Synchronous means timely, okay? So regular time intervals. And then we'll have peer-to-peer technologies. We might not have time for COBA, but we'll have peer-to-peer technologies. And COBA is closely related to that, but we'll focus on peer-to-peer technologies and examples. Now, so we'll go further ahead and look at the applications in data communications, applications in distributed systems. How do we have elections? Okay, because we need someone to control any interaction among peers. So how do we have an election? Then we'll have what we refer to as distributed mutual exclusion. So how do we ensure that only one person is accessing a resource? Okay, so that's called mutual exclusion. And then how do we ensure that we can manipulate data that is distributed? Data is in location A, data is in location B. How do we manipulate that data without confusing the system? So in general, those are the key things that we are looking at. So these other issues that I have here are basically, I just use them to ensure that we are on the same page. Okay, so basically we'll try as much as possible to see how we can stimulate the thirst for more information. And of course, I always have what I call open access. So in case you have any questions or some issues, or maybe we wanted something practiced, so you can always get back to me anytime. So I have written there in my office, but now I have a virtual office, so you can get to me through email. Okay, and then of course, like I mentioned, we can also do that through the different module leaders. Now, what I mentioned earlier on about this particular course, I said it can be very, very technical. And that's why I mentioned the background that we looked at, that was computer networks and operating systems. So it can be boring sometimes. It can be confusing. So where are the scientific concepts? So we are going to look at that and see which are the concepts that you can use practically in daily life, practically in your field, so that you can be able to move to the next level after practice. So the first thing that you want to look at here, what is your current view of the class? So this is important because that will help you, it will motivate you to be able to move. So I have this case here whereby you as a student, so where you're looking at basic concepts or just terminology, and that means that you will have a very narrow understanding of this. So I like the last one, where you have critical and appreciative understanding of the textbook, the lecturer, and the notes, and creatively use this. Why is this so? Because in actual practice, when you want to implement some of these things, it is not the theory that you learned, it's how creatively you use the information that you learned, such that you can be able to apply that. So that is the key why I'm saying, find a way looking at what we have here, motivate yourself to be able to look at it from the point of view that you can creatively, critically use that information. So there are just a few things before we move into actual practice, look at our class. I'm sure you'll find, and sure you'll have time to attend the sessions. Okay, of course, some of them are being recorded, so you can get that. There are several things about homework and assignments that I will maybe share with you. I'm still thinking about the best way, okay, to be able to do that. And basically, I'm open to people asking me questions during that time. So when you are having a homework or assignment, feel free to ask me, or sir, there's this particular thing here that is not clear. Maybe can you elaborate? I'm open so that people implement what they have, but they have all the information necessary to be able to implement that. So how do I organize my notes? So if you go on e-learning already, I have put our lecture notes from the first to the last class, so everything is there. I also have extra notes from other sources. So sometimes I find there's a concept that I explained in class, but there might be some underlying points, like I mentioned, that you might be required to know extra, but is not a key important thing, but you can be able to review. So I have they are called EX. I have a prefix EX, and prefix 1, 2, 3. So prefix 1, 2, 3 are my notes, and prefix EX, those are extra notes from other sources, from different universities and so forth. And then, of course, textbook. These are the textbooks that we have. Hopefully, if the things get back to normalcy, we'll have to access them. But most probably, there are several parts. Some of them might be obtained as PDFs. So we'll see. We can work together to see if we can find them. And these 3 books are key, especially the first 2. Most of our discussions will focus on the first one and support from the second one. Okay. So I will mention that, Peter, in a short while. So just okay. So in regard to the notes, like I was saying, I have that information, and I will share the enrollment key, but it's usually very simple. So those who can capture can, it's ICS 4104-2020, but I'll share that information later on. Okay, so that is accessible. You can be able to check that out. Then we have, okay, and then in terms of the assignments, I'm still thinking about the best way to be able to do this. It's not yet ready, so I will discuss and plan because we are still exploring several things. So I'll do that maybe by one or maybe by next week. And then, of course, cuts, the same thing. So we have to think about how well this can be done. So we'll see. And then, of course, exams are usually out of 60. Then we have our week to week. So this week, this one I'll run through quickly. So week to week, so we have the introduction to distributed systems. So then we'll move to communications. Okay. then we'll end up with 5, or talking about peer-to-peer technologies, week 6, network file systems, maybe week 7, processes, okay? And then week 8, naming, 9 and 10, synchronization, and maybe 11, we should be talking about consistency and replication. And then later, I think on week 12, where we need to stop, we'll be talking about fault tolerance. I think this one here, it's week 12, not week 13, week 12, okay, of teaching. So unless otherwise, I don't think it can go to week 13. So this represents our plan. And usually one of the things that I talk about when I start a course is that we need to have a very clear plan, because if you don't know where you are going, you can end up anywhere. So that's why I have a plan. So there might be a few things that will change along the way. Look out for them, but this is a plan. So basically it means that as you go through the course, once in a while you can come back and check on this. Like for example, I might have put deadlines here for the assignment when we started, but when I design and look at it, I might make a few changes. But there's one thing about assignments that I need to share very quickly, that whenever I give an assignment and I have a date given with that, but for a particular assignment, I always give 1 week grace period. So if, for example, the assignment was due today, then it means between today and next week on Wednesday, at such a time, you can submit anywhere in between. You won't lose any marks. But immediately after that 1 week grace period, it means that you start losing marks. So it means that if I have, and the deadline was today, you can hand it today, tomorrow, all the way until Wednesday. Of course, you can even hand in earlier, but you cannot hand in after. You cannot hand in after that 1 week without a penalty. Okay, so that is very, very important for you to be able to remember. So just as I put on this one here, I can be able to okay. There, maybe let me just check. So okay, so let me try and send the message maybe to everyone. Let's see if we have. So I have sent that on the chat. So check. If it's not, then I'll try to give another one. Maybe I ask the library to set it up. So can someone confirm if they can be able to access the notes? Try this one. Hyphen 2019 is not working too. Oh, the issue is something else. Okay. So fine. So I think we can be able to explore that. We can continue with the class and then okay. So fine. So let's just continue with our class and then we can be able to explore those issues. But the notes are online. So that's is good feedback to know so that I can resolve that tomorrow. Now, any questions so far? Maybe or something that you might want me to clarify before we now move to the introduction. Anything that you might want me to clarify? So I'll stop the sharing and see if someone has something that you might want me to confirm. Okay, so maybe we can pick up some of those issues or maybe questions later. So let me move to the introduction of the course. And so you can see, I hope all of you can be able to see my slide on the introduction of distributed systems. So, so to get to the point, what do we mean when we talk about a distributed system? So a distributed system is a collection of independent computers. So right now, as we talk, we are on independent devices. So it's a distributed system that appears to the users of the system as a single computer. Okay, so what it simply means is that those things are working independently, but the results are appearing. Like right now, I'm talking to all of you. It's as if you are on my computer. It's as if you are all inside my system. So, but you are in different places. So that's a good example of what we call a distributed system. An example, workstations plus a pool of processors, okay, in a department's network. Like maybe if you have, in our department, we have printers, we have workstations, we have servers and whatever that perform different tasks. So if the system as a whole looked and acted like a single computer, acted as a single computer. Now, the keyword here, okay, keyword here is acted like a single computer. So you are sitting on your desktop. You can be able to access files that are even different sides of the globe. They're accessible to you. You can do something to them. You can make changes. And it's as if they are sharing. So simply taking one part of your system, performing a task. Maybe it's a computation. Another one does the formatting. Another one does what? And then all the information is given back to you. So that can qualify as a distributed system. So there is what we call time sharing. So it means that each one of them is performing a task independently, but they are all combined together at the end for you to have a result. So that's called time sharing. So that will be an example of a distributed system. We also have other examples. Colaris et al. Says that a distributed system can be a network of computers. They communicate and coordinate the action. So we have one computer in one location, another one in another location. They are working independently, partially doing the work and passing messages to one another. Okay? And sometimes they can work at the same time, concurrent execution. And then they can be able to share the results. Then we can have an example of a distributed system. So they are concurrent execution. Now, the other thing that is very important from this definition of Colaris is no global clock. So if you're accessing a file from New York, file from London, file from different parts, I'm using different time zones. There is no clock. Your result is not impacted by the difference in the clock in those different parts. Okay, so no global clock. And the parts fail independent of one another. So if the part that is in London fails, it does not mean that the part in New York will fail, or the other part, or even the part here fails. No. So they fail independently. So the only thing that you can realize is degradation of performance. Or if a component that failed was supposed to give you a result, maybe that's when you realize that it failed. So that means that a distributed system has concurrent execution, no global clock, and components fail independent of one another. Now, this definition here must exclude what we call tightly coupled systems. Now, tightly coupled systems are systems that have maybe a shared memory. Now, if you have a shared memory, it means you store the information in the same location, you access information in the same location. So in that case, that is not distributed because it's one after another. So if we are sharing a memory, I will use the memory. Okay, let me use the term store. If I'm storing information from one memory and you want to access the same, we cannot store at the same time. We have to store one after another and vice versa. So in that case, that's not a distributed system. On the other side, they don't have a shared clock. Okay, if a shared clock, it means all the transactions have to be ordered based on that clock, regardless of where you are. So that can't be a distributed system. So when you are looking at this concept of distributed system, we must be able to forget or leave out tightly coupled. Tightly coupled means that if one part of the system fails, the other one has that impact. That's what we call a tightly coupled system. So, of course, that definition leads us to the definition of system of systems, the internet. Okay, so an internet is a good example of a a distributed system. So they are interconnected systems with one another. We can be able to access the information from one end to another, and they are connected. So the internet is a simple example of a distributed system. Okay, so when we let's look at another definition, and this is the definition by Tannenbaum: a collection of independent computers. Okay, so these are independent computers wherever they are, but to the users, they appear as single coherent system. They work together, single coherent system. Okay, so that means that they are autonomous. Okay, they have their own network, they have their own servers, they have whatever, but they are connected, so they are autonomous. And they use software specifically designed to provide integrated computing facility. So if I'm computing something, okay, and it has to be combined or served by several computers, so that's another example of a distributed system. So they're autonomous, and they have specific software designed to ensure that they work together simultaneously. Okay, one part works on this, another part works on this, and that means that we can now be able to combine that. So that's another definition of a distributed system. Now, so if you look at that, let's think about that definition. So if they are working independently, so you can see from what I have here, okay, so I have machine A, I have machine B, and I have machine C. And all of them each one is having its own local operating system. Okay, so that is autonomy. But for them to be able to work together, I mentioned in the last slide that they must have software that makes them possible to work together. And that is what now we have here as middleware and distributed applications. So these are softwares that can help these different autonomous computers to work together. So now, on the concept of that definition by Tannenbaum, we end up saying that, part of the software we need is what we call here middleware, and middleware extends to all these computers. Okay, it extends to all of them. Okay, it extends to all the multiple machines. You can see, like I said here, middleware and distributed system at the top there, and it provides an API. The API allows them to be able to locate transparently. Now, if you look at this term here, locate transparently across the network. locate transparently simply means that these systems here, when they work with each other, they are not, to the user, it's not identified. You cannot know who is working with you. It is hidden. So the term transparency, as used in distributed system, means it is hidden. Now, you understand from the normal language when you say transparent, I say it's room. But in the distributed system, when you say transparent, it's something that is there. I can use it, but I cannot just directly just look at it. So, and that is the reason behind it. For us to have a distributed system, we want to use machines, but I don't want to know where they are. That's why we say transparently. So they provide interaction, they provide services, and they provide that independent from the network services that are provided. So they are reliable and available always. And so some of this basically it means that, as you can see here, the operating system and network services are there to support, to help you. So middleware and other distributed applications run seamlessly across all of them on top of the distributed, on top of the local operating system of each computer. So in that case, therefore, they are able to ensure that all the applications can be accessed. Now, so if I just as an example, if you look at this diagram here, we have, for example, I can, like right now I'm using a microphone. So you can use displays, you can use game joystick, you can use keyboard, you can use mouse, and then you are having input. So that input, of course, let's not focus on the integrated circuits or kernel space. We'll talk about that later on. And then the middleware. The middleware you can see there. Okay, maybe let me use something else. So you can see here. Okay, we have here middleware, and this middleware runs across from all this, and then you can have input output. So the middleware allows you to have input output regardless of which device you are using. So speech recognition, gestures, user drivers, and whatever. Of course, there is latency, the time it takes, and then you can get your feedback on this side. So on your speakers, you can get on your monitors, you can Keyboard and whatever. So middleware supports that. So basically what you're saying, middleware is responsible to ensure whichever application, as long as you have that software middleware, you can be able to access any of that particular maybe application or any particular service that is being provided. Now that definition forgets or leaves out an important part. So let's look at another definition. This is by Lambert. Lambert, by the way, is one of the researchers who worked a lot on timing in terms of distributed systems. So we'll meet research by Lambert later on. And Lambert says, you know you have a distributed system, okay? You know you have a distributed system if a crash of a computer you have never heard of stops you from getting your work done. Think about it. Supposing right now you start downloading a movie, okay? And in the process of downloading a movie, you just clicked on some interface on that movie and it starts downloading. You even don't know the server and all the information. But if it breaks down, that's when you start noticing the issues. So now it simply means now you are depending on something, interdependencies. You are having a shared state when you're having that interaction. And then, of course, since your computer is still working, you have independent failure of components. So that means that, therefore, when you are talking about distributed systems, we also have the concept of partial failures. Okay, so Lambert put this very clearly so that now it can be able to be understood that when now some things happen somewhere, you might not notice until they have an impact on you. But later on, we'll discuss how does the distributed system do this. For example, if you start accessing your email on Gmail, you might not realize maybe the server has failed because the system, the network system, might have transferred you to another Gmail server and you continue accessing your mail. You might only notice delay, but your service is there. So that is what we call fault tolerance. So we'll discuss that, and it simply means that the system has a way of ensuring that it does not put all these problems to you, but the system can be able to handle. So that's called fault tolerance. So we have partial failures, and those we'll discuss later on. Now, so from what I have there, I want us maybe to discuss the advantages of distributed systems and what the motivation before we can look at some, I can now be able to pick a few questions and one on this. So let's start with the first one, advantages, economics. So this means that like right now, each one of us is on his or her own device, okay? So imagine a scenario where if we are using this, let me use a simple case of denial of service. If we are attacking a particular service together, we have that power of trying to put it down because we have a lot of devices connected. So, but if I was using one processor, then it means that it is not going to be effective because of the computing power. So it means that this concept of having distributed system allows you to have a chance of being able to combine. The other one is speed. All our devices working together, we can have higher computing power. Of course, this concept has gone a whole cycle. So when we started, we had mainframes, which were powerful. Then we had PCs, and we have mobile phones that are now powerful. Now we are going to what are called Google farms. Like, for example, now we have the cloud. So we are going back to the same thing, but we still have now the capacity to be able to using powers, the same computing power per device. So imagine each one of you computing some part of maybe task, and we combine the result. We'll do that very fast. Then, of course, inherent distribution. Right now, as we talk, you are spatially separated. We are in different locations. So inherent distribution. So you can actually work at home, work on transit, wherever you go, you can be able to work. So spatial inherent distribution. Reliability. If you have a mainframe or one server that is failing, it means that the whole service can stop. But in this scenario here, if we have a combined effort, so you'll find that some of the power that we lose is a smaller percentage. So we can still survive with degradation of performance. Hello? Is someone asking a question? Hello? Yes. Okay. So maybe let me get back to this. There was some interruption. I think, I don't know, was someone else was speaking. So the other thing that you can see from here is, in terms of this, we have incremental growth. Look at it as a scenario where you have your own organization, or let's say a small startup. Then when you start, you're in Nairobi, and then you have some people going, let's say, Thika, and then there are some in Mombasa. So you can have incremental growth, slowly, and you have added computing power, okay? Then you have data sharing. So the information can be stored in a shared common database. Each one of you doesn't have to have their independent databases, independent servers, and so forth. We can have device sharing. Okay, we can share expensive peripherals like printers, servers, and so forth. And then, of course, it allows us to have communication among ourselves. We can send email, we can have face-to-face, and so forth. And flexibility. I can be able to decide which areas of our network are not overloaded. And then I can simply say, let's take that information, or let's take the work to those locations. So these are some of the advantages. But of course, we have disadvantage. Software. Software is one of the areas that is a big problem. So little software exists that is at present. Development is there, of course, but it requires some improvement, some work so that it can be able to access nearly all the devices that we want. So basically, we are saying a little software exists, and we look at some examples of this. Then, of course, networking, it can saturate and cause other problems. And of course, security issues, okay? Security issues. So the moment I am on a network, I'm sure from networking, you know very well that now you are accessible to the world, okay? So this means that distributed system brings in these issues as problems. So for you to be able to implement this, one has to navigate in this. Now, since we're looking at that, what are the motivations? So from my last slide, therefore, part of the motivation of distributed systems is sharing resources. Okay, it's good. We can also personalize environments. Okay, that means I can use the environment that I'm happy about. We can have location independence. You stay wherever you want to go, and you can also be on the move. People and information can be distributed, okay, wherever you want. Performance and cost, okay. We can improve performance and we can reduce costs by buying simple devices to support. We can be able to organize our work in terms of modules. So I have one component somewhere, another component somewhere, and we can continuously expand to cover a wide area, okay? And if one part of the system fails, another part is available, so we increase modularity. And of course, scalability. Scalability means the growth. So instead of having the just in Nairobi alone, it can grow to other places. Someone is asking a question? Okay, let me pick up that in a short while. So before we get to this, before we look at pick a few questions, this is a good example of a distributed system. ATMs. So you may access ATM your account simultaneously. You can access from different parts and you still access your account. So that is an example of a distributed system. So, but concurrent issues can arise, and so we can pick up, that's a discussion we can pick up later on. So it means that we can have a central location, then we can have backup that is there. And in cases that are disconnected, we can also have, how do we handle outstanding transactions? Maybe you had transactions and something happened outstanding. So how do you handle that? And then network failure. So these are cases where we are going to look at how does a distributed system solve this one here. So I want to pick up questions there. And now that I'm picking up questions, maybe I'll stop the sharing so that I can see some of the questions can come maybe from, okay. So Timothy says, can you redefine shared state at inherent distribution? Now, shared state simply means, okay, let me use a good example. Let me say you have a file store, and that file store has a particular file. Now, if we access that file simultaneously, if we save that information, whoever has saved that information last will overwrite the information that was written first. So that is one location. So it's shared state. So when we have a shared state, it means all of us are accessing the same location. And therefore, in that scenario, we need to be able to say, if we are accessing the same location, how do we ensure that the information is not lost? So we have one. So all of us are connected, but we have one location. So like, look at it as a database. But each one of us, if each one of us is having their own databases, that's not a shared state. Okay? So the point is that shared state means that we access at the same time, same location, but we have to be careful in terms of how we save that information. So in a distributed system, we are saying each one was different and they were accessing the information elsewhere. So we have no problem that you're accessing this file and I'm accessing this file at the same time. Inherent distribution. Inherent means that the distributed system gives us an opportunity to possibly be able to distribute things. It comes with that opportunity to allow you to distribute. So for example, I can have a device here in Nairobi, and I can also have another device in Mombasa. Later on, I can now decide I want another device in Kisumu, for example. That's what we call inherent. So the opportunity to be able to distribute things, that's what it's saying. Another question, maybe something someone wants me to clarify. Okay, now, so the other thing maybe, okay. Waweru says middleware. Okay, now, middleware is basically a software that allows different devices to be able to communicate. Now, that software is available on all the devices. So when you send me your message, for example, you're using your device, that software is available there. When I receive the message on my side, I have the same. And therefore, whatever you had put down, if it was a picture or whatever, I can see exactly what you gave. So it does not mean that it's going to be interpreted. Otherwise, no. It just gives me an opportunity. So it gives me, it's a special, okay, let me put it, it's a special kind of application that is available to all the devices that can be able to access any of the services that are provided. So it's available, and the point is that it's exactly the same. What I mean exactly the same, that the software you have downloaded, let's look at it as a version. The software that you have downloaded version that is on your computer must be exactly the same that is on my computer, so that whatever you share with me, I can also be able to see it exactly the way you wanted me to see. So we have no differences in the way we can be able to see or view or be able to access whatever resource you're giving. Okay? Now, Waweru, maybe we're going to show some examples of middleware in a short while. So if I explain that later on and it's not very clear, feel free again to get back so that we can be able to handle that. Okay. Anyone else wanted something else that maybe they wanted to? Okay. Now, middleware and distributed applications behave exactly the same. They behave exactly the same. The only difference is that in distributed applications, any one of us can be able to decide an app, for example, and I put it up there and it's available. People can download and whatever. Middleware is now specifically for the network, on the network, so that it's running on top of the local operating system, which is on the local computer, and therefore seamlessly across all the devices connected on a network will have access to that. So in terms of behavior, middleware behaves exactly as distributed application. The only difference is that is on a network, and distributed applications, you can have them on your laptops and whatever. So this one runs on top of a network. Okay. Distribute as a shared state, not a shared state. That question is not clear, Timothy. Okay, maybe let me try to put it this way. Yeah. So when I said not a shared state, and that question that was coming up earlier on, that's what I was trying to explain. If you see the question that was, yeah, Timothy, you remember you said define shared state. Yeah. And so we said a shared state. So a distributed system does not have a shared, it excludes a shared state. And the reason is this: if you have a shared state, it means you have to work and then I work. We have to do it in stages. Now, a distributed system, you work and I'm working concurrent. So anything that has a shared state is not a distributed system because it has to be systematic, one after another. And that's why I said a distributed system excludes a shared state. So I hope this sounds clear. It excludes a shared state. So I was trying to explain a shared state earlier on, whereby things are being shared, and that means we have to access one by one. And that means that if we are accessing one by one, then we can easily, if I save on top of another, I overwrite it. That is it. Okay, so maybe what we can do, let's continue, then we can pick up a few questions maybe later on. But feel free to be able to reorganize some of those questions so that we can be able to reply to some of them. So if I go back to our slides, so what are the characteristics of a distributed system? So some of these things now, what we have explained, some of them are going to be, recap some of them. So a distributed system characteristics, key is resource sharing. So here I'm saying that basically, okay, you have an opportunity for us to be able to share clients and other members of the system via a network. Remember, a resource here can be several things. Can be a server, can be a database, can be a printer, things that can be shared. Okay, are those examples I've given. And so instead of each one of us buying their own server, their own printer, we can share. But to do that, of course, we need a resource manager. And basically, it has particular modules, policies to be able to do that. And of course, it has to provide an interface for us to be able to be manipulated by the clients. So I log on my computer, I can use I can see the interface for printer, a server, and then I can be able to manipulate. So resource sharing is one. Okay. The other one that comes directly after that, okay, okay, openness. Now, openness. When we say a distributed system is open, we are saying that you can incorporate services without disruption of the existing services. Okay? So already let's assume we have a service for a printer, service for a server. Things are already working, people are printing. And then now you decide, I want a service maybe for video conferencing. You can incorporate that new service without affecting the services that were going on. But for it to be considered open, remember this term here, for it to be considered as open, the interfaces that are there must be published. Okay? I'm sure you know very well, I'll use the example of maybe Safaricom. You remember when people wanted to do some of the maybe developments, so they had to give an API. So that is called publishing. So it means that you know that information, you know that interface, and then you can be able to add. So for a system, operating system to be called open, the interfaces must be available so that when you want to plug in something new, you can be able to do it. The next one, in terms of this, is concurrency. And distributed system means that we have concurrency. That means that access to this must be synchronized to avoid things like lost update, incorrect summary, lost update. So let's put it this way. Now, if I update something and then you update on top of it, mine is lost if things were not synchronized. Or that read simply says you are reading a value that has been updated but has not been updated on the server. Or so you have a value that is dirty, so it's not yet updated. Or when you are summarizing, you have incorrect values from other places. Some are updated, some are not, and you have incorrect value. And repeatable read, you read a value. If you try to read again, you get a new value because it has been updated. So the distributed system must have concurrency to ensure that these changes that you are making, if you access at any one point in time, you will always get the latest value synchronized. That's why another example of an example of middleware is Java, okay? Java software. So, and that's why I'm sure you have used it to program, you have that part synchronized. So that's exactly what you are trying to say, okay? The other part of this concept is scalability. Scalability means that your distributed system can grow in size, and when it still is growing, it can still efficiently utilize software and hardware additions. Now, so supposing we were 100 people connected on a server, okay? A distributed system simply says that I can add more people without each one of us feeling a strain or degradation in performance. Now, that means, therefore, that a distributed system, like we said in openness above, you must be able to know software and hardware additions must be possible. So scalability, usually this goes towards, the easiest way to understand this is the geographical growth, okay? So it was in Nairobi alone, then we moved to Mombasa, we still add, we have not removed the ones that were in Nairobi, but we still can be able to add new components. Okay. Now, the other thing about distributed system is what we call fault tolerance. That simply means it tolerates faults. It can handle errors. Okay, it can be able to handle errors. Okay, and when they occur, and even the user might not even realize errors occur. But for us to be able to do that, so we ensure there is enough hardware and software to handle this. So software recovery aspects are there. We have hardware recovery aspects. So hardware, we have redundant. So if I have two servers, one fails, another one, it immediately takes me to another server. As a user, I might not even realize that the server failed. The only thing that might happen, it might be slow. So I'm thinking maybe the network, but I might not realize maybe it was a server. And we also have software. So some of the errors can be handled through software and some can be handled through hardware. So we look at techniques later on of how this is actually done. And then the other thing about this one here is transparency. A distributed system must be transparent. Now you remember those who are here when I started, transparency in distributed systems simply says that you hide unnecessary details from the users. Okay, you hide unnecessary details from the users. As a user, I don't want to know that the computer I'm using is in New York or is in London or is in Kisumu. I am not interested. I just want my service. Okay, so transparency means we hide unnecessary details. So there are several aspects. Remember, here I've said unnecessary details. It means it does not add value in what you are doing in terms of what you want to get. Okay, like for example, if it tells you the computer that has failed that you are using, this is the API, it's not useful to you unless it's only one, and that means now you know there's a problem. But if there's another computer to help you, it just transfers you. Another server to help you, it transfers you and you get your service. So there are several aspects of transparency. The first is location transparency. Clients do not need to know the location of servers. Now, this is important because if you look at it, let's look at it from a simple point. Okay, if you knew the servers of a very, let me use security issues, maybe servers for a very important national security installation. If you know where those servers are, that is not, okay, let's assume that you cannot access using your network. So you don't want that to be known, and therefore, even the users don't know, okay, where that server is. So that's what we are saying. I will still use it, but I don't want to know where it is. Okay. The next, we have other transparencies, okay, that we'll talk about. So, but it brings me to this. I want to repeat this again. Transparency. Hide all irrelevant details, system-dependent details from the users. The next thing, create an illusion of the model users are supposed to see. Now, for example, right now as I speak, I only have access to my laptop. And this is what I'm seeing, okay? But I am connected to all of you in different locations. So the illusion here is that I am seeing everything here on my computer. I don't know where you are. I don't want to know that. I don't want the details. The point is this, that it ends up basically simplifying. Because imagine if now you are giving me, I am in this location, I'm using this kind of software, I'm using this kind of maybe device, and it uses this software. That's unnecessary. So you end up, at the end, transparency requires a trade-off. You want things as simple as possible, and you want things to be effective. So sometimes there are certain things you might not be able to hide as much. Like for example, if you are only using one maybe server and it goes down, you might simply get information that tells you that that is it, okay? But to make sure that this is done well, so we are trying to balance. And so we look at some examples later on, how do we ensure that it's effective? Because if you put a lot of information, it becomes unnecessary noise to the user. So the objective of transparency, therefore, okay, the objective of transparency here, you have a logical view of a physical system and you reduce the effect and awareness of the physical system to a minimum. What you are seeing is what you might be thinking that is all that I have. Okay, so you can reduce that to a minimum. Okay, maybe let me. Yeah. So basically, to a minimum, what you can be able to see, but you are still, remember, you still have the functionality working. So we have this slide here gives us examples of transparency. I mentioned only one, but I will repeat some of them. So we have access transparency. Okay, access transparency here simply says hide differences in data representation and how the resources are accessed. Now, from your maybe second year when you did computer organization, you know we have different computers represent data differently. Now, even if the computers, they represent the information differently, okay, we can still be able to communicate. You send me a message in the data representation that you had on your computer, but I will receive it in the format that is on my computer. So we have hidden those differences. Location, I have already explained that. So we simply say that hide where a resource is located. The third one is migration. Okay, so migration. Hide a resource may move to another location. So today you are using a server. It is in, let me use Fatma, for example, to make it easier. So you have a server in phase one. Then ICTS decides, no, I think we have created a new room somewhere in phase two, or maybe phase three, for example, a nice location. We are going to move that server. As a user, when that server, it will not tell you it has moved. You will still just get your service. Okay, so that is called migration. Then we have relocation. A server may be moved to another location while in use. Supposing you set up, now laptops are very powerful these days, and even phones. Supposing I set up my laptop as a server, okay? And maybe let's assume even right now, I have a mobile modem, okay? And I start moving. I will still continue with this discussion, okay? And you will not even know that I am moving. But physically, I have moved from where I am to a different location. I might be using a different mast of Safaricom to be able to access that information. So relocation simply says a resource may move to another location while in use. Replication, hide that a resource might have multiple copies. Okay. You have a server, like I mentioned earlier on, you have one server that is giving you services, maybe a mail server. It fails, like Google Forms. It fails. It fails. Immediately, it fails. It takes you to another server. You'll still get your service. So, but the other one, when it comes up, it will still be working now, set up. So the two of them are working. So when you access a Gmail, for example, you'll access one with the server that is closer to you. If that one fails, there's another one. So that means that we have multiple resources, multiple copies. And in fact, one of the first things that occurs that if I have change on this server, what will happen to the next server? Okay. We'll discuss that later on. So there's a way where that information has to be updated. They have to work in. And if a server comes up, it has to be updated so that if the next person accesses that one, they have an update. They have the latest information about that server, about the changes that were made. The other one is concurrency, hide that a resource may be shared by several competitive users. Server, an example. Let's use a database server. You're using your work, you're doing your work somewhere, I'm doing my work somewhere. We are using the same server. So the only time it might want to ensure that it ensures that there is synchronization if we are accessing the same file. But if there are different files, no need even to be able to synchronize because they are independent. And then we have what we call failure transparency, failure and recovery of a resource. So I'm sure as you have been using servers, some of them have failed and they have come up. Nowhere along the way did it tell you that the server has come up, unless it was only one server. Unless it was only one server. I'll go to the charts later on. So if it's a question, please keep that. We'll get back there. So unless it's only one server, that's when it tells you, oh, I am up again. But if there were multiple, it failed, it took you to another one, and then you continue with your work. So failure and recovery of a resource is hidden from a user. And the other point here is persistence. The other point is persistence. So basically, we are on persistence. We are saying hide whether software resource is in memory or on a disk. Okay, so when you are changing files, okay, you are updating files. From computer organization, we learned that disk takes a long time to update. Of course, memory is fast. But as a user, it's not telling you whether this information is on your disk, is on the disk. And here I'm talking about those large servers that have disks, or is in your memory. Okay, maybe let's say random access memory. It's not telling you. Okay, so persistence means that now if you close, it persists. So later on, when you come to open that particular file, you can be able to see that file again. Okay, so that's what we call persistence. So we look at this and apply this several times. But before I give an opportunity for questions, some issues have arisen here that we have to be very careful about. In my discussion, I have mentioned several different entities. Entities are, let me call those devices you are using, for example. Okay, so how do we name them? Okay, how do we uniquely identify so there is no confusion? So we'll discuss that. Now, as we are discussing this, we have to communicate. How do we ensure that there is communication among the entities? So, by the way, naming is a whole topic, so that we look at how this is done. Communication is also a whole topic. Now, the other thing about this that is very clear that we have to know is that the software must have a well-defined interface. Remember I said published. Well-defined. So that means that the users can be able to, remember, the communication of anything over the internet goes through layers. You have your application layer at the top, and at the very bottom you have the physical that converts my voice into binary. So the communication, the software that we have must have well-defined interfaces that allow each one to communicate to another layer so that information can be passed. So from right now, I'm using the interface, okay? But that goes all the way to my computer, okay? And then that is converted into binary before it gets all the way now to my device, and then, of course, getting over the network. So we must have a well-defined structure. We look at that. And then, of course, the other issue, as you design, this must scale, okay? How far can it grow, okay? And growth cannot be arbitrary. So if I want to expand, there are certain things maybe I might have to add, servers, networks, and whatever. So we have to think carefully how we design that, okay? And of course, we also talked about partial failure. We need to be able to ensure that in this case of partial failure, we need to know, we can detect something has failed, we can mask some of those failures, we can tolerate those failures, and we can have recovery without necessarily the users knowing that. So these are design issues that are very, very important when from what I've discussed, that someone must be very, very, very clear about. Now, again, in a way, I'm recapping, but I also looking at it in terms of design. Location transparency, okay? Location transparency, okay? Users cannot tell where resources are located, okay? Migration transparency, resources can move without changing. And by the way, I say they can move while new. I forgot to mention without changing their names. And that's why when you access next time, the server might have moved from phase 1 to phase 2, from Nairobi to Mombasa. You'll still access. The name is still the same. Remember the naming. Replication, okay, here, users cannot tell how many copies exist, okay, and of course, as scalability is implemented, we will have multiple copies. Concurrency, okay, multiple users can share resources automatically, okay. I don't have to be able to say, now I want to use the resources, the software will handle that. Parallelism transparency, activities can happen in parallel without the users knowing. You don't want to know that who is also using the system at this time. As long as you have the hardware and software not to degrade performance, then you have no problem. You don't have to worry about that one. Okay, and then the other thing about design is how do you design now your independent device? So like right now I'm using a laptop. So on my laptop, how is it designed in such a way that it can handle this? So there are two ways that this can be done. We can have what is called monolithic. Monolithic simply says it's a larger program. It handles everything. Okay, so maybe let me get down to there. File system, directory system, full process management, system calling, some of the tasks, some of the things you did in operating system. So that's monolithic. So it means that it's doing a lot of things, and this can be a problem in distributed systems. So as we compare, we want a distributed system to be such that you can do things as fast as possible. You can do things without overloading the operating system. Remember, we said that distributed applications and middleware are running on top of your operating system. So if we overload the operating system, it will not be an efficient distributed system. And therefore comes in the concept of microkernel. Keep it small, user-level servers for the services. So if we do that, therefore, our discussions or our communications will be through inter-process communication. So if I want to discuss with you something, maybe by email or maybe by chat, it is inter-process communication. Some elements of, so let me clear that so that it's easier. Some elements of memory management, but it is on a specific part, a small part of what we are doing. Not all of them are at the same time. And a small amount of low process management and scheduling, a small amount. And low level input and output functions are done at the kernel. So microkernel means that it basically distributes the things that are being done to other things, to other applications. Monolithic means it performs those tasks itself. Microkernel says, if you ask me a task, I say, oh, this task can be performed by this application. I take you to that application to handle it. And I wait for the next task and take it elsewhere. So that is microkernel. So keep it small, user-level servers, inter-process communication. So some element of memory management, because I want to know that if I have given a function to A, I don't want to know when it comes back so that I report back. So I cannot forget about everything. So I have to remember something. Then related to that, in terms of that design, is reliability. So reliability means basically, it comes from the concept of availability. If something is available, I can say it's reliable. And that's why we say 99%, 99.9%. So that is reliability. But it's supported by fault tolerance. If something fails, another one comes up, picks up the services that are being provided. So that is why someone can simply tell you 99.9%. Okay? That is basically, it doesn't mean nothing fails. Things fail, but others take over those services. Okay? So if you think about reliability, you might say, for example, instead of using directly my phone connected, my phone, I might have a wireless that is not connected to, let's say, power. So I have charged it, I'm ready for it, and I have my laptop that is already charged. Okay, so if I was using the ones that are connected directly to power, if that one goes, this one picks up. So what you will notice is degradation, a slight difference in time, but still we'll still be able to convert, to be able to continue with our conversation. So that's reliability. Performance, when you are talking about performance, you are saying that how are things done? So there are certain things we can have them separated into smaller things, minor modules. Okay? And we have also larger modules. So if something is large, it means that for me to get a result, I will have to wait until everything is done. Now, that can be inefficient, but smaller tasks, I can have them done. So this one is returned, this one is returned, this one, as I'm waiting for another one. So that improves performance. I can be able to say a result that has come in, I can use it for another task. So I improve performance. But if I have coarse-grained parallelism, I'm saying I will have to wait for the result finally. So that is not a good way of designing your system. Scalability, okay, of course I talked about that. So we know that there are potential bottlenecks if we are using centralized system. If we have a single server, if it fails, everything goes down. So centralized component, centralized tables, centralized algorithms, anything that is centralized is a bottleneck. So we use what we call decentralized algorithms. So no machine has complete information about the state, so they are distributed. No machine makes decisions. A machine makes decisions based on local data. So in your location, you make a decision based on your information there, on your local system. I'll make mine based on my local system. Okay? Failure of one machine does not ruin the algorithm. Mine will still run. Like right now, if let's assume your Zoom fails wherever you are, mine will still run. So that's an example of one machine does not ruin the algorithm. And then, of course, no implicit assumption, okay, of a global clock. So let me assume someone maybe in a different country, different time zone. Again, they are listening to me at this particular time, getting the same information, but we are on different time zones. No implicit assumption of a global clock. And that's how the distributed system should be able to work. Now, one of the things that has made this possible, okay, I think I'll stop here for maybe, let me finish this slide, and then I stop here, I pick questions because I think our time is nearly over. There are certain things that have made possible for the distributed system to work. Okay? Now, I'm sure you can see some of these ones here. Okay? So we moved from 8-bit, 16-bit, 32-bit, 64-bit. We had the X family, we had 8K family, alpha chips. We have clock rates that have moved. In fact, 4.0 gigahertz plus. I'm sure you know some that are even higher. Okay, so powerful microprocessors. And remember, we say distributed systems, we combine several. So fast things are combined, so they are powerful. So that is one aspect. Those are advances that are there. The next one that is also has made this possible, networks. Okay, so we have local area networks, wide area networks, wireless networks, mobile networks, 3G, 4G, 5G, maybe maybe near future locally. Okay, so this means that we have powerful processors and we have networks that make this possible. And then, of course, transfer rates. Okay, more than even 1 gigabit per second. Okay, so that means that with the networks, or with maybe fiber and or the rest, whatever, all these different kind of connections, it has made possible for us to be able to do this. So I can stream a movie right from the other side of the globe, and I get the information up and fast. So you can imagine if we're using a very old computer, that would be a disaster. You can't even enjoy them. And then, of course, secondary storage. Okay, so in 85, secondary storage, 10 MB, 90, we had 250, 93, 1 gigabit. Okay, so I'm talking about even things like laptops. 4GB, 97, 2000, about 20 GB, 06, maybe 8 at 120, 08, 240 plus, 18, 500 plus. I'm sure you know of some. Now, let me look at this as computers. Now, I'm sure you know now laptops, not laptops, mobile phones that are even more powerful than some of these old computers. And that's why you can stream right on your mobile phone. So these are some of the advances in technology that have made it possible for us to be able to use, implement distributed systems. Okay, so when you're looking at distributed system, and that's why I mentioned from the beginning about networking and whatever. So it's important to remember a distributed system runs on top of these things. Okay, processors, networks, and storage. So I think I want to stop there and pick questions so that we can be able to stop in a few minutes. And since this was the first lecture, I don't want it to be much longer than that. So let's go and check questions. Any questions? Rodney, I've seen your email. So you are that's group B module leader. So I will hand maybe group A and the other one for BTC. Okay, so you can send that information. So any questions that you want me to respond to? If you want that question, maybe the others even to hear, is you can just feel free. You can use one by one. I can give you an opportunity to ask. Okay, just raise up your hand, and I'll see your hand, and then ask you to give you an opportunity to ask. Caesar, what do you mean an e-learning platform? Because are you talking about e-learning as we have it? Because if it's e-learning, there's information there. There's information there about our notes, and I'll put other things. So I don't know unless that's what you're asking. Okay. Another question? Okay, so what I'll do, I'll see if I can troubleshoot tomorrow and ensure that I have the correct information on e-learning, and therefore you can be able to access. And therefore, when you come even for, we have our next lecture, please ensure you have the notes, so that when I'm explaining, you can be able to maybe easily go back and check something so that you can ask, and I respond to those questions. So I'll try to do that tomorrow. I think by next week that should be done. And like I said, all the notes are there from the beginning to the end. All the extra material is also there, so I have put that. But I'm still thinking about the best way to put up the assignments and so forth, so that I can also be thinking about it. So I can give you some information about that next week if it will have been set up. Okay, anyway, Group A, please, and BTC, send me your module leaders. I want to communicate with them on some issues to be able to make sure that our course is efficient. Okay, so if there are no maybe questions, thank you very much for being attending the class, and then we can pick up next Tuesday. I think it's 3:15. Next Tuesday at 3:15, and then we can be able to continue with our discussion. Feel free to pick questions that you want us to recap during that particular time. So otherwise, I think thank you very much. So we can stop there.